So my presentation is about autonomous driving 2.0 with a focus on what should change in our approach to AI. But first of all, why do we need a change in AI? If we look at the spectrum of the current solutions, we see that existing AI already works quite well when you speak about high compute ADAS and robotaxis. For these two verticals, we have in high compute ADAS, we have a predefined ODD, and we have enough compute. In the robotaxi, the problem is also more limited. We have a geofencing, and we have enormous sets of sensors. We have LiDARs, we have HD mapping, so the AI problem is a bit more contained. It's a bit more limited. However, when we look at the extremes of the spectrum of the problems, we still have a major challenge on the AI side. So one extreme is making ADAS systems affordable for low-cost or regular cars, using only vision only, and many times using just one camera. And the challenge there is that we don't have LiDARs, we don't have radars, we don't have mapping, and we must run on extremely low compute. The other extreme, of course, is the ability to take the AI one step forward and go beyond the predefined ODD into the autonomy domain. And doing that with relatively simple sensor suite. Of course, LiDARs and maps are very important, but they should be used more as a redundancy, as a fail-safe. And the challenge of the AI on the autonomy side is to enable human-level AI, to use vision, and by using vision sensors, basically to reach human-level capabilities of perceiving the environment and making the right decisions in real time, also for the long tail of the edge cases. So today, there is a traditional approach, which is basically called the modular or compound approach, that divides the problems to two basic building blocks, the perception and the decision-making, or in more granular approach, perception, path planning, actuation, and also using a localization as a redundancy. But the main principle here is to break the problem to two parts, understanding the environment and then making a decision, two separate models, two separate building blocks. And in the last half a year, Tesla and a few other companies started to shift away from this approach. I will speak briefly about the disadvantages of the compound approach and why the companies are shifting to what is called the new generation of AI, the end-to-end approach, where there is just one building block, one single neural network, from pixels to actuations to steerings to brake. So basically not helping the neural network, not helping the AI to break the problem to steps, but letting the AI, unleashing the AI to solve the problem end to end. So first, let me explain why the main train now believes that breaking the problem between perception and decision-making is probably not the right approach. When we break the problem to first perception, we end up in a situation that we have to identify a lot of things in the image or in this situation, in this scenario, that most of them are not very useful. So most of the time we have those bounding boxes and a lot of those attributes that we as people, we know that they're not very interesting for making a decision. It's too much information. But on the other extreme, there is a long tail of situations, those are more rare situations, where we are actually missing those different elements that we would expect from the perception. For example, we would like to know if this pedestrian is distracted or not. We would like to know what is the intent of this motorcycle, but we are missing those attributes. So because we don't have the feedback loop between the perception and the planning, actually the perception is not aware what is useful for the planning, for the decision making. And we end up with an average solution that most of the time produces too much information that is not useful, and in many cases, that are rare cases, doesn't produce the required information for the right decision-making progress. Another problem of breaking the problem to these two models, the perception and decision-making, is that we have to test the perception as a model on its own. And for this, even if we overcome the problem of training those systems, like in the case of Autobrains, if we have a self-learning approach, still we need to validate those systems and to test them. And for this, we need to generate a ground truth. We need to label a lot of data. And that's why companies that are focusing on the classical approach of ADAS employ thousands of people or sometimes outsource the problem of labeling. But there is a huge heavy lifting of labeling data in order to validate those systems. The end-to-end approach, in a certain magical way, solves all these problems. We don't need to break anymore the problem to two pieces. We don't need to help the AI to define what is interesting. There is one network that takes us from pixels to the expected result. And all we have to do is basically collect data, collect driving examples, and let the system figure out what is the right decision on its own. So basically trust the AI and this process of training, data collection, and validation. But this new generation of AD2.0, the new generation of AI, leads its own challenges. And the challenge essentially is in the long tail. Similarly to the problem of perception that was a generic solution, now we have a neural network that is optimized to solve the problem end-to-end, but still it is optimized for the generic case. So the way to train neural networks today is to collect a lot of data, to label this data or to collect driving examples, and then to train the neural network to minimize the average error over the entire training set. That's basically the state of the art today. And as a result, almost by design, the network is missing this long tail of edge cases because they are diluted in this very large training set. This is the major challenge today of the end-to-end network, similar like Tesla. If you look at Tesla, they have millions of miles, the most powerful computers, and still in the edge cases, they don't have a very good solution. The approach to this problem today is this cycle that you can see on this slide is basically to feed more data, to increase the neural network capacity, so more compute, and to feed more examples. But in order to solve this edge case, it means that basically we are talking about exponential climbing in terms of data requirements and compute requirements. And that's, of course, a major challenge to the industry. So we believe that the end-to-end approach is going to face a similar problem of diminishing returns as we've seen for the perception model in the modular approach. I think very interesting observation is that the problem of driving is a very good fit for humans. So when we are looking for the right AI to solve the problem, at least as a baseline, we should look at humans. Once we reach the human level driving, it's very easy to take the system to be superhuman with more sensors, more redundancy, more mapping, more compute, shorter response time, and so on. So the first goal is really to understand how humans are driving, and from this inspiration to identify what are the gaps in the current AI approach and the approach that will actually work well for full autonomy, including scaling to this long tail of the edge cases. If we think about the human brain, there are several interesting aspects. So the first aspect is the human brain is extremely adaptive. Unlike the AI system, we don't have a fixed system that functions the same in different scenarios. The brain adapts itself. The second interesting observation about the brain is that the brain doesn't use all its resources all the time. The brain has a lot of mechanisms similar to routing. So the brain finds what are the relevant areas for this specific context of driving. If we are getting into roundabout, a specific circuit in the brain will be activated. If you are driving after a truck on a highway on a heavy rain, a different resources will be allocated. So this adaptivity and this ability to identify the right resources and to route them is one of the key principles of the brain that we implement in our technology. So to summarize a bit the three current main approaches today, the first one is the compound or the modular approach that started, the first days of this approach came from robotics, and it made a long way in the ADAS. It's a very good fit for ADAS, where you can predefine the scenarios, you can define your expectations from the perception model, you can define the object list from the perception to the path planning. But once we go beyond that, beyond this predefined ODD, we have a challenge. And so, like I mentioned, Tesla and others are advocating today for the end-to-end, one giant neural network, which is hitting the wall, as we see, when we scale to these edge cases. The third approach, which our company is developing, and I would like to present to you today, is what we call a modular end-to-end approach. We do believe in the ability of neural networks to solve the problem without breaking it in a human engineering way, without breaking it to perception and decision-making. But instead of having one big neural network that is optimized for the average case, in the case of Autobrains approach, we have a large ensemble, so a large set of small neural networks, smaller brains that are optimized for different scenarios. Scenarios like I mentioned, whether it's following a truck, getting into roundabout, or stopping in front of a crossing pedestrian. One of the unique advantages of this approach is that when we want to update the system or to fix an error, we don't have to retrain the whole system. One of the challenges of the AI today is when we fix a certain problem, we immediately expose the system to new problems. If you want to update the system with a new feature, we have to revalidate the whole system. But if we have a memory of many smaller neural networks, and we fix one or we add another neural network, we don't have to revalidate the whole system from scratch. A few words about the architecture. So what you can see here, from the left side, we have an input. The input is vision only. It's those scenarios, those visual episodes that are injected in what we call a perception router. So unlike in the end-to-end, we do have a model that is a perception, but the objective of the perception is very different. It's not about to identify bounding boxes and identify every pixel in the image. It's more about understanding holistically what is in front of us, very human level-like, and based on this understanding of the scenario, to find in the available ensemble of smaller neural network, the right neural network to solve this problem. We call these smaller neural network skills, in a similar way as humans have skills or different driving skills. Those smaller neural networks are end-to-end, so similar to Tesla approach, but they're not pretending or trying to solve the whole AV problem. A single neural network may just focus on a problem of getting into roundabout, and another neural network on a problem of following a truck on a heavy rain. And so the flow is images in, perception router picks the right skill for the right scenario, and then the skill gets, again, pixels in, steering, acceleration, and brakes out. So fully end-to-end approach. Just to describe the whole ecosystem of our system, what we provide to our customers is the ability to control, to the OEMs, is to control their AI stack. What we are providing is the AI that produces those smaller brains, those skills. We call it a skill factory. So essentially, a skill factory is the AI that is able to take a narrow scenario that is produced by this perception router and to develop, train, validate, and homologate those driving skills. And so the process is really incremental. We can have a car with a certain amount of skills already on the car that is running, but it has a certain coverage of autonomy. The perception router can identify a missing skill, send an input to the skill factory to produce the skill, and once the skill reaches a certain maturity in terms of its KPIs, it can go to the shadow mode, to supervised mode, and eventually reach unsupervised mode in the car, all in a very incremental way. So just to summarize the advantages of this approach, we believe this modular end-to-end approach is optimized for the long tail of the edge cases. And that's where we see the challenge of the industry now. I believe that the 95, even 98% of the autonomous driving problem is solved Where major players are stuck is in the last mile, in the last few percents. The second problem, if we're thinking about end-to-end, is explainability. We cannot trust a black box without any ability to trace the result, to understand why a certain decision was made. In the modular end-to-end approach, we have a very clear responsibility for every function. Every driving skill, every AI agent has its own objective. We can trace it and understand the problem. The third advantage is the low compute. So while we have enormous amount of resources, we have this ensemble of neural networks, maybe even more than one giant neural network, the amount of resources that are actually being used running the car in a certain time is a very small fraction because of this routing. It's actually less than 1%. So I can speak a bit about numbers. If out of the 400,000 skills, about only 5 neural networks are actually being used. This dramatically reduces the computational requirements of the system. Shorter cycles and incremental learning, as I already mentioned, that's one of the advantages. We don't need to retrain the system. We can update it on incremental level and trace and debug it on every small step. So this is just to summarize the advantages. Thank you.
Thank you, Igal. I think we got a good insight into the new era, into the new approach of AI in automotive. And here are some questions of our audience. The first is, Tesla is betting on vision only because they say the world around the car, traffic signs, e.g., is built for being seen with a human eye. Do you think their approach will work best?
I think we shouldn't neglect any mean that can help reach autonomy. So if we're talking about radars, LiDARs, HD maps, all of them are very important. But when we are developing the AI, I think the most important part is first to reach the human level capability. And to do that, we need to focus on vision only. And then to use the rest of the techniques as a redundancy, as a fail-safe, to get beyond the human level.
Thank you. And the second question, how do you see the future of collaboration between car manufacturers and technology companies like your company in the field of AI?
So I think the collaboration, of course, should be more closer. And that's why when we think about this type of collaboration, we understand that this type of technology is strategic and critical to OEMs. And the OEMs want to own their AI stack. They don't want just to license and run black boxes. And so that's why we define this concept of a skill factory. Basically, it's an AI that produces smaller AIs that can be launched and shipped into the cars, but they are visible to OEMs, and the OEMs have full control about what is going into the car and their ability to improve it and fix it.
Okay. Thank you very much, Igal.